Okay. Okay, welcome everyone. I would like to introduce Katie Human of Ceres, who will introduce our next press conference.
Hi, thank you so much for sticking it out for the entire day here. So I'm Katie Human, the Director of Communications at Ceres, which is the Cooperative Institute for Research in Environmental Sciences, and I can't see a thing, sorry. Really, again, thank you for sticking it out here. So our idea is that science consumers or stakeholders can be much, much more than that. Increasingly today, scientists are working to engage communities and other users in the co-production of science. So you'll hear 4 stories today from our panelists who are going to try to be, representative of hundreds of scientists at AGU this year who are presenting work that aligns with this theme of co-produced science, working with those who benefit from your research. So I'm going to let them introduce themselves, except for Dan Ferguson, who will kick us off.
Okay. Can you, Katie, or I can do it.
There you go.
Okay, let's start at the beginning. Okay. Pointer's up here?
Yep.
Yes, it is. Okay, so my name is Dan Ferguson. I direct a research program at the University of Arizona called the Climate Assessment for the Southwest. And what I'm going to talk about is a project that's been going on for the last couple of years with some colleagues of mine at the University of Arizona and the Hopi Department of Natural Resources. The Hopi Tribe is a Native American community in the Southwest. Oh, sorry. Okay, so here's where we are. This is the geography that I'm working in. This is the Four Corners, so-called Four Corners region of the U.S. Southwest. The only thing you really need to know from this figure, this map, is you're looking at where weather stations are. Okay, and so there's a couple things to notice. This large polygon is the Navajo Nation. The smaller polygon within it is the Hopi Reservation. And the thing you want to notice is that there aren't really any weather stations. So this landscape is about 30,000 square miles, so it's quite large. That's about the same size as Ireland, the country of Ireland. There are not many weather stations just surrounding this 30,000 square miles. And you'll notice that on the Hopi Reservation, there are none. And on the Navajo Nation, there are only a couple. And they're actually on federal inholding. So essentially, there are no weather stations. And these are long-term stations on these lands. So, and this is why, this lack of data is why this collaboration with the Hopi Tribe started. The Hopi Department of Natural Resources was very concerned that this lack of data meant that they didn't have information monitoring their lands for drought, which is a big concern here. And they contacted us to work on this problem. So this is what it looks like. This is a farm field in Kukultnvi, one of the villages. It's actually the capital of Hopi. And this is a pretty common image in the summer. So the Hopi people have been in this place for more than 1,000 years, and they've been dryland farming, which means they don't irrigate. And so that means, for the purposes of drought and climate research, that means that they, one, need rain in order to get crops to grow because they don't irrigate. And the second thing is they're really good at doing that because they've been doing it for about 1,000 years now. And so when they contacted us because they were concerned about drought, we took it quite seriously. Literally, if the people who are world known for growing crops in a dry place are worried about drought, we should probably pay attention. So this is also what it looks like. This is the southern part of the reservation where it abuts the Navajo Nation. And that fence line, in fact, is the dividing line between Hopi and Navajo. And what you're looking at is these large sand dunes are essentially inundating parts of the reservation. And so these dunes, this landscape scale change is happening as a result of a combination of drought that's been about 2 decades of very dry conditions there, and land use, essentially cattle grazing. But these dunes are really destructive for lots of reasons, and these are practical challenges if you're a government dealing with drought, trying to manage for drought. These are very practical problems you're facing. For example, this fence line is buried in a dune, so the fence line will be effectively, not very effective soon. Also, these dunes are inundating roadways, which is expensive to clear. This used to be plants, which cows ate, which they are not going to be eating anymore because it's now buried in sand. So there's a lot of impacts from drought that a government, in this case the Hopi Tribe, has to deal with, and that's part of what we were engaged on, is what they do. So these are essentially the 3 problems that were the centerpiece of this collaboration. This work started in 2009. It's been going on for quite a while, and through a lot of collaborative work, we came to these 3 problems that we could work on together with the Hopi Department of Natural Resources. So the first is this data problem. There isn't any data. The second is they have a drought plan. the Hopi Tribe has a drought plan, but it's essentially ineffective because it doesn't really represent how drought's experienced there. And what I mean by that specifically is it was written by a consultant, and it's just sort of a template drought plan, and it didn't really integrate at all the way that people there experience drought. And then finally, as a result of the lack of data, there's really no local drought information to inform decision-making for the government itself and for the Department of Natural Resources specifically. So those are the problems we worked on. Here's the stuff we did. So what we wound up doing was we tried to figure out what they do. So what does the Hopi DNR do? What are the problems they're confronting? How do they manage information? What kind of information do they develop themselves? What kind of data do they develop? What do they do with it? That kind of stuff. And so this is my colleague Mike Crimmins, who is my main collaborator on this project. And this is Rick Nastofi, who's a technician for the Hopi Range Management Office. So we spent a bunch of time with these guys. We went to a bunch of meetings with them. We hung out in the DNR. We tried to understand what drought meant for them in terms of management. We also did a bunch of interviews across the reservation to try to understand how drought is impacting the communities. So the first thing we did was try to understand the context for drought. So as a result of that work, we came up with this scheme, which is fairly simplistic, to be perfectly honest, but it seems like it could work really well, which is take whatever information the DNR is collecting that may tell you something about drought conditions. Again, remember, there's not really weather stations, very reliable long-term records. So what are they collecting? Like, for example, Rick and his colleagues, they monitor range conditions. That seems like it's a pretty good way to keep track of drought conditions as well. So we said, well, why don't we have a 2-page summary with their capacity, their human resources, and stuff they could do. They decided they could do it quarterly, so every season. Produce a 2-page summary for drought stakeholders, basically, on the Hopi Reservation. The front page of which would be local information, whatever they think is useful, whatever reflects the problems that they feel like they want to keep track of, they want to monitor. That would be on the front. And then Mike and I and our colleagues at University of Arizona would produce regional information for the back. And this would include stuff like the U.S. Drought Monitor and other data that we can get access to. So the idea is local, and then contextualize it with the regional stuff that's available. So this is sort of the science that's available, and this is the local observations. And then finally, what we did was we did science, too. So this is just, I just grabbed this figure, which looks funny on this particular plot, but whatever, from a paper that's forthcoming. It actually doesn't matter what it says. The point really is that what we did was, as a result of all this interaction with the Hopi DNR, we as researchers learned a ton about drought and sort of, it matters when it rains, for example. It matters if all the rain comes in 2 storms in October. If you're trying to get soil moisture recharge, that screws you. That doesn't help you at all. It may help you grow some grass for branching, but maybe not. Totally different story than if your precipitation, you might add up to the same normal average precipitation, but when it comes and how it comes makes a huge difference. So we've been doing a fair bit of applied climatology now as a result of this interaction. So we understood the context, we came up with a scheme for a sort of local drought information system, and then we've done a bunch of research to try to understand drought in the region better. So who cares about this, right? Why does it matter? I think it matters because, and as Katie said in the introduction, AGU, more and more you're seeing talks where it's this kind of work that's engaged with communities. I think it matters. This particular case is an interesting example in my mind. It's my work. Partly because this is a really complex place. So this is one of the Hopi villages up here on this mesa, and this is a lovely summer storm coming through. It's a very complex topography, it's a very complex climate, it's a very complex social and cultural system, and drought is an extremely complicated hazard because it really has differential impacts depending on what you care about for precipitation. So what? Well, in this particular case, science is not the solution to this problem that they're facing, right? We're a part of it, and of course I made this up. This is not quantified. But in my back of the envelope, I think maybe 25% of the questions that need to be addressed are going to come from stuff that we can do, the science community can do. But the rest of it is not science. It's stuff like these local observations that the managers are doing. It's the values that are embedded in what you monitor. It's the political decisions they have to make. It's all that stuff. So in this particular case, science is a small fraction of it. The rest of it is really important, but together we've learned a ton, and I think this is my really corny figure, and I'm sorry, but I'm done. I think what we've gotten through this project now is a way better understanding of how the system works, the climate system here works, and how drought works in this place. Hopefully, the Hopi DNR has gotten what they needed out of it too, and our collective knowledge has been improved. And so it's not, the title of my actual talk tomorrow is not just consumers, because the idea here is the Hopi DNR was not just consuming information we were producing, they were helping us learn stuff along the way too. And that's it. Thank you.
All right, I'm Jeffrey Deems. I'm a research scientist at the University of Colorado in Ceres, where Katie hails from. I'm partly at the National Snow and Ice Data Center and partly at the NOAA Western Water Assessment, which is sort of a sister organization to what Dan runs down to our south. I'm showing you the title of my talk slide from Thursday, not to be impressive with a list of names, but more I want you to notice the list of logos and affiliations there. This is a very much a collaborative project amongst scientists and technicians, as well as the end users of the data, the snow safety team at Arapahoe Basin Ski Patrol, and the local avalanche and highway resources in the state of Colorado. So I'm taking you to a much finer scale than Dan was just talking about. We're looking at individual slopes that produce avalanches, and those avalanches threaten skiers at ski areas and people who drive on the highways in Colorado. And we're using a new technique, or a new application of a technique called Lidar, or laser scanning, to make maps of snow depth in complex terrain, and using those maps to support these avalanche control operations. This is what these maps look like. On the far right over there on the top is a color-coded map of snow depth on an avalanche slope. You can actually see a couple avalanches in there. And HS means height of snow. That's snow depth from 0 in the greens, or very, very shallow in the greens, up to 3 meters or above in the red there. And just below that is snow depth change between the accumulation from one storm on that slope. On the left here, you can see what I've termed post-control snow depth change. In other words, the ski patrol went out there and lobbed a couple of explosive rounds up on that slope, and it brought down the avalanche that you can see there. So the pink areas around the avalanche represent increased snow depth change from the storm that put snow on the mountain, and then the whites and then the greens and blues represent the decrease in snow depth that happened due to the application of explosives on that slope, which triggered that avalanche. So we've been looking for, as a LiDAR application, this is fairly straightforward. It's just a change detection application. We go out, we make a surface elevation, we make a second one and subtract them. I'll show you more on that in a bit. It's really the application and the engagement with the end users that's the new product here. And I'll show you a couple of case studies of this. In one particular example, in the winter of 2015, we helped the snow safety team at Arapahoe Basin plan where they were going to place their explosive shots in the terrain. We went out in the morning, made a snow depth change map, sat down with the patrol, and actually looked at the areas of snow accumulation on that slope. Some of those areas were fully expected by them because it follows some sort of conventional patterns. Other areas that were a bit of a surprise to them, including this spot right here, which was an unusual snow drift and unusual wind direction. They went out, put a rocket round on that, and got an avalanche to run. That would not have happened without this data set. They would not have placed the explosive in that location. So good case study of helping them plan their routes. Another case study, this is from this past winter in 2016. Showed up in the morning, and there's a bunch of new snow everywhere. It looks like the snow on the east wall terrain here has accumulated enough for them to do a round of avalanche control. So we, similar to the previous study, made a snow depth change map, and in looking at this and sitting down with the ski patrollers, decided that there wasn't as much accumulation as it looked like to the naked eye, and they made the decision not to shoot on that day. Not quite as sexy as scan it and shoot it, but on the other hand, it was an important operational context. They saved some money in explosives. They saved, it made the improved safety for and limited the exposure to explosive material by the ski patrol, and was a great, I think, case study in really was unexpected on that day. We've also been working with the snow safety team there to help them plan their ski area expansion. This expansion is ongoing. Construction will begin this winter. This terrain here is currently outside the ski area boundary. They're expanding to include that. It's very complex terrain, above tree line going down into the trees. They've decided to manage that terrain by installing a tramway network. There's a series of cables, and they lower explosives down on these cables to affect the starting zone of the avalanches. They designed this network initially just using expert knowledge, so how they know snow accumulates on the landscape. And then we evaluated that using some new snow depth maps we produced with the laser scanner. And as a result, they completely redesigned the tramway network. So we're seeing both of them in the lower left there. The red lines are the initial tramway network that they designed, and the yellow lines are the new network that they will be installing starting this winter. So this provides not only an opportunity for the initial design of infrastructure, but now going forward, we're going to continue this effort so that we can start evaluating how well this infrastructure is working as they start implementing it in the future. Along similar lines, we've been working with the Colorado Department of Transportation and the Colorado Avalanche Information Center to evaluate some new equipment that was installed on the Seven Sisters set of avalanche paths that hit U.S. Highway 6. This is just over the hill from Arapahoe Basin. They manage these paths to keep the highway open. They'll shut the highway, do avalanche control, and reopen it. Conventionally, it was done with explosives like Arapahoe Basin is using. There was an accident a couple of years ago where a round exploded in the launcher and severely injured some people. As a result of that, they installed a new network of remote operated exploders that are up in the start zones. As a part of that, they're wondering how effective this new array is compared to their old system. So we're making pre-storm, post-storm, and post-control maps to help them evaluate how well those exploders are releasing snow. And we're seeing, in this case, as in the maps on the previous slide, some decreases in snow depth from avalanches triggered by these systems. So again, an ongoing effort with the Department of Transportation to help them evaluate the effectiveness of this new tool. I mentioned the general process. It's kind of it's a fairly straightforward workflow. We go out either in the snow-free time or pre and post-storm and post-avalanche control and conduct laser scans. This is the tripod-mounted survey instrument. We then convert that data into elevations. We make elevation maps of the terrain or of the snow-covered terrain and just do a vertical subtraction to produce either total snow depth, which is snow on minus snow free, or two different snow depth maps to get a change in snow depth over some interval. This is fairly straightforward. We're doing it in this instance with a terrestrial laser scanner, a tripod-mounted scanner. The same thing works from airborne systems. Tom Painter will talk about an application of that type of technology very shortly here. So backing up to the bigger picture, we need to know where the snow accumulates on the mountain, not only to plan where we put in situ applications or in situ infrastructure for avalanche mitigation, but where to plan explosive placement. The conventional methods of doing this rely on expert knowledge and familiarity with the terrain. The Lidar mapping allows us to quantify the distribution of snow across the landscape and really work with the practitioners to bring that very precise, high resolution knowledge into their decision-making frameworks. Thank you.
So Katie, is it okay if I just turn my time over to Jeff? I love listening to Jeff Deems talk, and especially about Arapahoe Basin, because I grew up skiing there. So here's the title that the JPL press office really did not want us to use, but it is true. We had the intention of partnering to kill uncertainty in snow water management, and Jeff is part of this program from the very beginning. And it's a tale of two lasers and the visionary water managers in the California Department of Water Resources, Hetch Hetchy Water and Power. So if anybody's been drinking water not out of these things, but out of the tap, we've scanned that water with our lasers. And various irrigation districts, the U.S.A., the Kings River Water Authority, utilities, Metropolitan Water District down south, and then of course NASA, and the U.S.A. again. So I'm going to start out with the end result, and then go back to where how we got to this. What we're showing here is the modeled or predicted inflow of water from a particular date in the spring out through the end of July, so out through the end of runoff, which is absolutely key to the distribution of water in the western U.S., and I'll show you in a second why that's the case. It's key to the distribution of water. It's key to hydroelectric generation and the various applications thereafter. And this is versus the actual accumulated inflow to end of runoff. All right, so we have an absurd R squared of 0.99, and this was generated by our partners at the Hetch Hetchy Water and Power, the city of San Francisco's water supply. And it took them, in the first couple of years, it took them a few weeks to send us these plots because they were sure they had screwed up and plotted an ASO product versus an ASO product, because you don't get a relationship like that usually without screwing up. So remember this 1% uncertainty as we go forward. And this is all driven by the results coming from the Airborne Snow Observatory, which I'll describe in a second. So in the western U.S., the mountain snowpack provides about 75% of the fresh water supply that falls as precipitation in each year. In this particular shot, we have, this is out of the original Airborne Snow Observatory, water flowing off here towards Los Angeles, down through the Los Angeles Aqueduct. And then right here on the other side of this boundary, this ridge, is the water flowing off to San Francisco. It's an interesting juxtaposition of their water supplies, given how far apart they are. But that shows you the tentacles that reach into the mountain snowpack. It all really began with Dr. James E. Church, who was a humanities professor at the University of Nevada, Reno, who set out to try to answer the question as to what was controlling the level of Lake Tahoe. And at that time, consistent with the theme of this particular press conference, he went to work with the operational folks to ultimately develop the federal snow sampler, or what we call in the business the Mount Rose sampler, to plunge it into the snowpack, pull it up, weigh it, and tell you how much water there is in the mountain snowpack. Now, to this day, and in fact back in 2015, where our partner Frank Gerke was out with his bodyguards, or rather the governor of California, it is the tool of choice. It really is it has been the backbone of water management and water prediction in the western U.S. all of this century. Fortunately, in 2016, he got a little more snow, and so he was praying to the gods for that. But what this has given us, and I'm not going to take you through it in detail, but what it tells us is that the uncertainty in forecasting how much water is going to come between April and July, so during that big snowmelt pulse, the uncertainty in that, about half of the time, the uncertainty, that forecast error, is more than 20%. That's a lot of water and a lot of money. And 1 in 5 times, it's more than 40% error. So that's a huge impact and huge uncertainty, and there's an enormous amount of hedging that goes on and inefficiency in water management in the western U.S. because of the uncertainties in the measurements. So beginning in 2011, I had a conversation with Frank Gerke, who I showed you there, who's the California snow groundhog. You see him in the newspaper every April 1, describing the snowpack. And I said, Frank, I think we can put together the technologies from our NASA investments that can lead to reducing that uncertainty in our understanding of the mountain snowpack. And so as Jeff described, we put together a scanning Lidar, so it's a dual laser system, but looking at the ground, but blasting along 15,000 feet off the deck and flying at 200 knots. And then right behind it is an imaging spectrometer, which measures the reflected sunlight from the snowpack. And that tells you how much sunlight is absorbed by the snowpack. Why does that matter? It matters because about 90 to 95% of the energy that goes to melting snow in the spring comes from absorbed sunlight. All right, so we coupled these together. And when I described this to Frank, he said, yep, I think you're right. Let's do it. And so that partnership began in the spring of 2011. And at that time, we were talking about flood mitigation, because 2011 was a huge year in the Sierra Nevada. And our program manager at NASA headquarters likes to claim that we kicked off the drought by starting the ASO program. So the ASO program is not just the plane, though. It's the acquisitions with the plane, it's flight planning, it's also the data processing. And an important component of this that was driven by that partnership is a 24-hour turnaround of products. And originally, our software team whispered to me that there's no way in hell we're going to be able to turn these around in 24 hours. It'll be several days to maybe weeks. But in order to be relevant for water management, we had to turn the products around quickly. And so that's been one of the really important pushes of this program. And then together with that is the real-time modeling. So being able to take the model or take the measurements that we have, and this was a real struggle for us initially, was we provided these maps of the spatial distribution of snow water equivalent all across the landscape to our hydrologic partners, our management partners, and they said, that's really cool. What the hell are we going to do with that? Because they were built up around a century of these very sparse measurements. And so we've been working with them on various fronts, and central to this has been our work with the U.S.A. Agricultural Research Service to bring in their distributed modeling, and we're weaving that in now with the state of California to implement across the state. So subsequently, we had Frank, so here he is on the plane. These are not masks, they are, or decorations. They're oxygen masks flying on the plane. And Frank was a flyer on the aircraft, and his presence was really important as we were learning how to fly the basins in an optimal way. And then more recently, partnership here with the Hetch Hetchy Water and Power, the Turlock Irrigation District representatives here, the Modesto Irrigation Districts, and the California Department of Water Resources. This is all ongoing. It's essentially every week that we're having conversations going forward. This is what one of the maps looks like. This was in April of 2014. This is the Tuolumne River Basin. This is the Hetch Hetchy Reservoir above O'Shaughnessy Dam. This is the water supply for the city of San Francisco and other Bay Area municipalities. And going back to this plot, so again, this is the total amount of water that's going to be coming out of the basin, or I should say coming into the reservoir. And remember, no longer are we running into the 40% uncertainties. We're down here in the single-digit percentage of uncertainties. So we really are killing off those uncertainties. Some of the quotes from our prominent water manager partners, Wes Moynier with the Turlock Irrigation District said, you know, Tommy, what you're doing there with ASO is creating new reservoirs without the need for lawsuits and environmental impact statements. And that's just because we're reducing that uncertainty and reducing the hedging that happened in the inefficiency. And Steve Haugen from the Kings River spoke to how he could now sleep in the spring in what was otherwise a horribly uncertain time always for these managers. So the final slide I want to show you is the ramp up now of the modernization really of the water management program related to snow from the California Department of Water Resources. And you'll see the Airborne Snow Observatory here at the center. We have the field measurements ongoing, satellite retrievals, and these research community partnerships that they call out. And just recently, NASA Applied Sciences established the Western Water Applications Office, which has the intention and the funding to help us to carry the NASA technologies related to water across this threshold into full application. And ASO is one of the central components of that program. So now I'm going to pass it on to Karim Ali, who will give you a fantastic talk as well. Oh, no, it's fine.
So,
It's hard to follow the eloquence of my colleagues from the biophysical sciences. My name is Karim Ali Qasim. I'm professor of environmental and indigenous studies at Cornell. I'm going to tell you about our project, which includes, of course, colleagues from the United States, China, Italy, and Germany. I'm going to talk about building anticipatory capacity for climate change at the level of communities using ecological calendars. So we're doing this work because indigenous and rural societies are at the vanguard of climate change, even though they are not the primary contributors to this change. It is having a direct impact on their livelihoods and their food systems, as well as our well-being, because 70%, FAO estimates that 70% of the world's food system still depends on smallholder farmers and herders and fishers. This lack of predictability in terms of seasonal change is creating a debilitating anxiety. And our work is trying to deal with that anxiety. And the challenge is not just an intellectual one. It is also an issue of justice, because these communities did not contribute to the causes of anthropogenic climate change. And we, many of the scientists actually at this panel, come from communities and societies that in fact did. So, what are ecological calendars? Imagine, what if the 5 minutes that I have with you today is different? What if time is unique? What if the 5 minutes I have with you today are different than the 5 minutes when your firstborn child arrived? And what if time is flexible? And what if time is relational? If we reconceptualize time in that way, we might be able to build anticipatory capacity for climate change. Let me explain. In a normal year, using the Gregorian calendar, a flower appears in May, and we seed, and we reap a great harvest in September. In a moment of climatic variation, there's early rainfall, and the flower appears in April. But we wait to seed in May, and we don't reap such a great harvest. But if we followed that seasonal cue and seeded when the flower appeared, we may have a wonderful harvest. Ecological calendars are about seasonal cues, appearance of a migratory bird, nascence of a flower, appearance of a specific insect, the last day of snow cover, the breakup of ice on a lake. These biophysical cues inform livelihood activities, such as when to plant crops, when to move herding animals, when to celebrate a particular cultural festival, and so on. Think about this for a moment. If we are to propose any adaptation strategy for any type of change, that strategy would have to be grounded culturally, socioculturally, and ecologically in the context where you're hoping to adapt strategically. So we're working in 6 sites across the globe, in Standing Rock Sioux Nation in North and South Dakota, at the Lake Oneida watershed in upstate New York, in the Pamir Mountains of Afghanistan and Tajikistan, in the Alai Mountains of the Kyrgyz Republic, and in the Kungurshan Mountains of Xinjiang, China. In each one of these regions, we're working with herders, with farmers, with maple producers, with trappers, with hunters, to develop anticipatory capacity that is context-specific. So how are we doing this? We're working in partnership with communities where climate science, ecology, and place-based knowledge are working in tandem. So when we're talking about interdisciplinarity and transdisciplinarity, we don't mean that the climatologist is having a conversation with the ecologist, who is having a conversation with the botanist, who is having a conversation with the ethnographer, who is having a conversation with the educationist. All of them are working in tandem with the herder, with the farmer, with the fisher. And this approach is facilitating development of hybrid knowledge that can help us anticipate change. So as this project has just begun in the past year, we expect concrete, implementable proof of concepts in these diverse ecological, geographic, and cultural zones, where we can take ecological calendars that are context-specific and relevant. We hope to develop curriculum to facilitate transfer of this intergenerational hybrid knowledge by developing curriculum specific for schools as well as undergraduate students, so that this knowledge remains dynamic and continues to respond to the change at the local context. To have an international conference where we bring scholars and communities together to exchange information. When we were funded by the National Science Foundation of the United States, China, its equivalent in Germany, and its equivalent in Italy, immediately we started receiving notes from other places that were interested in engaging in similar work. And we asked them to keep their projects separate so that when we get together, we are able to share that information. We also hope to develop an online platform so that this sharing of information and knowledge between communities and scholars continues. And finally, like any National Science Foundation project, we need to have peer-reviewed journals. Thank you.
Okay, so now we'll open up the floor to questions from reporters.
Hi, I'm Alex Woodsey with Nature. My question is for Dan Ferguson. Can you talk a little bit about what you learned from the Hopi, if anything?
Wow. Nice narrow question. I think the main there's a bunch of stuff. We didn't get into a lot of, like Kareem's work, we're not working with citizens, we're not working on traditional ecological knowledge, for example. So a lot of what we've taken away is from the DNR staff, who are all Hopi people. So they do have really good local knowledge. So among the things that my colleagues and I have been learning is, as I mentioned, sort of specific ways that drought plays out in that place. And that matters because for us as a research group, because the work that we do is place specific. We work in the Southwest. A lot of us work in the Southwest. And it's really easy to look at something like the U.S. Drought Monitor, which is a weekly produced, basically science produces every week, to try to characterize drought on the landscape, and just believe it. And what we've learned from working so closely in such a small community with no instruments, basically no weather stations, is that we're getting it pretty wrong. And so one of the takeaways that I've gotten from this work is, boy, it really, you really gotta look closely to figure out how, in this case, drought has an impact on a place. And it's traditional livelihoods there, so it's not a cash economy, so it's not even easy to track the impacts because there's no I can't just go to USDA and get crop value data. So you literally have to kind of work there to understand what's happening. So, that's a long way of saying mostly what I've learned is really closely tied to, like I mentioned, the complexity of drought, the complexity of drought in a really complicated landscape.
It was about to fall. Sorry.
Thank you.
I wanted to drop and kill our ears.
And the way that a government has to deal with those complexities. So this is a very small government. It's not rich. They don't have endless resources. So it's sort of like, wow, that's a lot of complexity that they're wrestling with. What's the role for us? What's the role for science? It's actually, like I mentioned, it's pretty minimal, but there's stuff we can do for sure. We've been now we've taken it upon ourselves to try to educate, our side of the equation. Come to AGU, publish papers saying, hey, look, we kind of didn't catch the story right. Specifically stuff like the drought monitor. That is actually tied to USDA payments at this point for ranchers. We found that Hopi, some of the research that I've done, nobody there is actually getting that money. They're not applying for that. So they're not even part of that system. But the drought monitor is triggering policy, and it's essentially wrong in that place.
Any other questions from reporters in the room? Yeah.
Hi, my name is Margaret Benner-Smith. I'm with Environment Magazine and Weatherwise Magazine, and I have a question for Dr. Selekasam. I'm sorry, I think I'm pronouncing that wrong.
Just call me Kareem.
Kareem, there we go. I just wanted to know, I know you're at the start of your project, you said you're only a year in. Have you seen any effects of climate change already, or do you anticipate seeing many effects from climate change as you develop these ecological calendars? Are things changing for all these communities?
Right. So we are working in regions where we already have relationships. And so we have been observing in Central Asia dramatic impacts of climate change over the past 10 years. In fact, it was they and our work in the Arctic with native communities that got us down this path to look at climate change. And we have been observing these changes, and the very idea of using ecological calendars is an idea that emanates from there. It was not something that we articulated. They had first suggested it to us in 2006, and then we began to investigate them. We found 500-year-old Persian manuscripts, Russian ethnographic data, German ethnographic data, and our own interviews that then pointed to us these ecological calendars. What is really exciting about this is that they are just as relevant in the Pamir Mountains of Central Asia, where we have demonstrated that history, as they are relevant at Standing Rock or at Lake Oneida. So there's a universality of conceptions that are very, very useful here. So a conversation can occur.
Any other questions? Yes.
My name is Whitney Spivey from Los Alamos National Laboratory. My question is for Daniel. Is the lack of weather stations on Navajo and Hopi land unique, or is it standard for native land in the Southwest? And if that's the case, how accurate is drought monitoring across the Southwest?
Thank you for that question. It's a problem. The lack of instruments on Indian reservations in the U.S. is a known problem. It's tied up in lots of history and bureaucracy, to be honest, why it's still like that. So in Arizona, I'm at the University of Arizona, which is in Tucson in southern Arizona. Very close to us is the Tohono Nation, which is a very large reservation that straddles the U.S.-Mexico border. Basically, you see the same phenomena there. So, and it's rife across. I have not done the analysis to quantify, this specific problem, but it's very easy to look at where stations are, and you can basically pick out reservations from looking at those maps. The problems that cascade from that lack of data are just endless in a way. And so, the drought monitoring problem specifically is what we were tackling. There are ways around it. There are stations around the reservation, and there are gridded data sets available that interpolate between the points and stuff. And so the reality is that for some stuff, it maybe doesn't matter quite so much. But the challenge that we found working directly with the Hopi DNR is that they have really specific challenges, and it's very heterogeneous. That landscape is very complicated, and so, we've been hearing for years from working there that they keep saying that the rains are changing in the summer and they're coming in these strips, and what that really means is that they're very localized storms. So you really need a more rigorous set of observations to capture that diversity. And that matters because it might be you have to close a range unit or something, or remove cattle from a specific range. So the lack of data is a big problem. And it does impact the way that, and I think there's a huge equity and justice issue underneath of all of what I'm talking about. Because there's basically a data equity issue, right? It's not a coincidence that Indian reservations are places that there's not much data for this. And as Kareem alluded to, I mean, it didn't allude to, it mentioned outright, you know, Native peoples around the world, indigenous peoples are the one who are really highly exposed to climate change. And this lack of data and this lack of, in the U.S., for sovereign nations who have to manage in the face of this, you know, data is a pretty key tool that's missing in a lot of these places.
Can I add to that? From a snowpack standpoint, this data issue in the lowlands it has a broader implication. The dust that blows out of the lowlands usually deposits into the next topographic obstacle it runs into. So Dan is a producer of dust that falls into our snow in Colorado and accelerates the snow melt there. And we've pushed for many years to try to understand the physiographic controls as well as the climatic controls on dust distribution. Why do we see a lot more dust in one year than another year? And then also the increase in dust that we've seen across the last 15 years into the Colorado Rockies, coming from these areas. What's been controlling that? And this reaches also to the Pamirs, the Karakoram, the Hindu Kush, where you have these proximal deserts which are experiencing severe land disturbance, lowering of water tables, just through activities as well as the broader impact of climate change. So we have a desperate need to be able to understand these regions.
So what may I add to that? So what we have done is precisely said, all right, what is missing? And in our case, we're actually putting in the climate stations. We're putting them up in the mountain and in the valley, and putting in soil monitors, which the Italians and the Germans are keeping track of, except in China. Our Chinese colleagues have to do it. And so we're now trying to build that data set, and we're asking ourselves the question, how can we fill in for the gaps that have occurred? Whether it's in the United States because of absence of data, or the collapse of the Soviet Union, because many of those are former Soviet republics, at least 2 sites. So how do we fill in? And so we're built a team of a group of people who are modeling based on the data we're just starting to collect in Central Asia. And I think that's the only way to go, is when we identify gaps, to go in and start filling them in with the appropriate technology we can find with colleagues from around the world.
And it's the implication of what I'm going to describe is not perfectly germane to the topic of our panel, but if you look at the lowlands and you look at the high elevation regions, both of them are quite connected through this particular process, and the work that Kareem is doing in looking at those populations. If we lose glaciers from, say, the mountains in Central Asia, then late summer runoff largely disappears. That base flow disappears. And there are populations there that are right there on the edge already. But if they lose that flow of water that they've relied on for centuries, then they're going to have to move. Where are they going to move? They're going to move to some place where there's water. Well, if there's already water there, there are already people there, right? So all of this tied together has tremendous geopolitical and conflict implications.
Any more questions from reporters in the room?
Hi, excellent talks from all the speakers. I'm John Karachuski and Groundwater Resources Association of California. This question is for Thomas. Your work is very interesting, but given the drought, how much of that snowpack either sublimates, it goes from snow into the atmosphere and or sinks into the ground because of the soil moisture deficit and doesn't make it to the reservoir? So can you comment on those issues?
So that's a really good question. And so So the physical processes themselves, we understand well. So what you raised in terms of soil moisture deficit is really important. We can have intense drought years in the mountains. So there's very little precipitation up there, very little snowfall to fill in that soil moisture. We can follow it up with a big year of accumulation of snow, but when it melts, we don't get the big pulse of runoff that we would expect, because it has to go to filling up that soil moisture before it can run off. So we understand those physical processes themselves, but the geography of those distributions is what we haven't known. And with the very sparse measurements from these index sites from the federal samplers and then the snow pillows that came along in the 1970s and 80s, we really didn't have the complete information with which to be able to answer that question. To be able to answer the question of how much recharge are we getting, how much sublimation are we getting in evapotranspiration, how much are the plants using, because we simply didn't know how much accumulation of snow there was in the mountains. So there are several publications coming out right now and several presentations here at the meeting that are using our results to finally be able to constrain and answer those kinds of questions. So it will be over the coming years that we'll be able to answer those questions and to get at recharge and to be able to get at a handle on what kind of groundwater replenishment we might be able to get out of the big years that we hope are coming.
Okay, any more questions from reporters in the room? Do we have any questions on the chat? All right, that's it. We're done for today, and we'll reconvene at 8:30 tomorrow morning. Thank you, guys.